There's a Mexican snack that's named sponge. I don't eat it. It's marshmallow based. I'm vegan, so that's not a direction I go. But yet I receive every so often packages of sponge from avid science aficionados in Mexico because they know that I'm a great fan of the word sponge, because it's an acronym for the atomic elements that are necessary for life, right? Sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen. And in particular, two of those, hydrogen and oxygen, when they come together to yield water, water is an absolutely essential part of the emergence of life, or at least life as we know it. It is far too strong to say that where there is water, there is life, but it's probably true for our form of life that locations where there is not water, has never been water, are locations where there is not life. So as we look out into the universe, and we now are aware that around the hundreds of billions of stars in each of the hundreds of billions of galaxies, there are planets. When we try to imagine whether there's life out there on those other planets, part of that question comes down to whether or not there are places in the cosmos that have water and have those essential atomic elements that can come together and yield organic molecules. And so this question of whether or not we are alone, this profound question of whether or not there is life out there, whether there is one example, a few examples, or a ubiquity of examples, requires that we really go out and explore, and at least explore in as great detail as we can those heavenly bodies that are near enough for us to do more than just look at them through powerful telescopes. And that's what this program is about. NASA, as well as its partners, have set upon spectacular and daring missions to try to answer this question of life in the universe. And we're going to focus upon 3 such missions today. One mission going to near-Earth asteroids, another going back to the moon, and another already on Mars. And our goal is to try to get to the state of the art on where our thinking is on the ubiquity of water, the ubiquity of organic molecules, and the possibility that there is life out there. So we're going to begin with the mission to a near-Earth asteroid, and we have a couple of leading scientists to help us through these ideas. Let me bring in Phil Bland, a planetary scientist who is director of the Space Science and Technology Center at Curtin University, and also director of Australian node of the NASA Solar System Exploration Research Virtual Institute. Hello. Welcome, Phil. Also joining us from Tucson, Arizona is Jessica Barnes, an assistant professor in the Lunar and Planetary Laboratory at the College of Science at the University of Arizona, which led the Osiris-Rex mission that we'll be talking about in collaboration with NASA, and which already has some samples from an asteroid in hand, as we will see. So welcome, Jessica. All right, so let's kind of just begin, if you will, at the beginning of this particular mission. So which asteroid, Phil, are you focusing your attention on, and what's it like out there?
So the mission went to asteroid Bennu. Bennu is a near-Earth asteroid, so it's the majority of asteroids in the solar system are in between the orbit of Mars and Jupiter, and their orbits stay out there. Sometimes they get kicked into what we call the inner solar system. Bennu's one of those, about the size of Sydney Harbour Bridge.
Now, for those of us from New York, maybe there's another analogy. How big, is that? Jessica, do you have maybe an American analogy just coming from the other side of the water there?
Not so much an American analogy, but it's about 510 meters across.
Right. And Jessica, why this particular asteroid? In fact, can you give us a sense, how plentiful are asteroids out there? Is it sort of one of a few or one of a great many?
So that's a great question. There are millions of asteroids that we know of. There are also, we suspect, millions more that we can't yet see. And Bennu was chosen for some specific reasons. So Bennu's a near-Earth asteroid, like Phil just mentioned, which means it doesn't orbit far away. It's between the orbit of Earth and Mars, which means it's close to get to. You don't want missions that last decades and decades and decades, so it was easier to get to. Also, we needed an object that was small enough that we could orbit safely, but large enough that we could actually touch the surface to collect a sample. And as I'm sure we're going to talk about, Bennu's composition is, we suspected, was carbon rich. And so that's what led to it being, one of 5 asteroids that we could reasonably get to in a short enough time span, sample, and had the right chemistry that we would be able to answer the questions we set out to address.
And when did planning for this trip begin, Jessica? Is this a long time in the works or relatively recent?
Oh, a long time. I would say probably in total 2 decades. So Osiris-Rex wasn't selected on its first shot. It was actually selected on the 3rd time. The original PI of the mission was Dr. Mike Drake, who was actually the head of the department that I'm currently in. And Mike shepherded the proposal through the preparation stages, and it got selected in 2012. And only a few months after it was selected, Mike actually passed away. And so the deputy PI of the mission, who was his apprentice or apprentice, I guess, in the department, then took over the mission from him. So it's a long time in the works.
Yeah. And how long have you been working on it?
I joined the mission just after I joined the University of Arizona, so I've been part of the team for just over 4 years now.
Right. And so, Phil, where is this asteroid? We say it's near Earth, but how far away is it? How long does it take to get there?
So it flew, Artemis flew in 2016. I think it took 6 years to get there, Jess. Now I'm going to screw this up. Seeing the launch, I was in the US to see the launch.
Oh, you were?
Yeah,
Wow.
It was fantastic. That's the only launch I've ever seen.
And it launched from where?
From Cape Canaveral,
Yeah.
and it's exactly as everyone imagines in terms of how awesome it is. You're on the causeway, you feel the shockwave.
Yeah, you feel the rumbles. Yeah.
It was just fantastic. And then, so it's actually, it's a privilege to be involved in several missions. This is the first one I've been involved in from before the launch all the way up to bringing the material back and then analyzing it in our lab. And we work really closely with Jess and her team on that. And she's good enough to have what she's called satellite meetings. So she rings us at a horrible hour, Arizona time, to make it actually a decent hour in Australia. Thank you in public for that.
And so the name of this, Osiris-Rex, it does sound something from like a Transformer movie or something. So, Jessica, is there meaning to this particular name, or just a marketing ploy to get people interested?
Maybe a bit of both. No, in serious, there's a reason behind it. So, Osiris-Rex kind of is what it says on the tin. The acronym stands for origins. So we want to understand our origins. So how did life on Earth emerge? What were the conditions needed for that? Are asteroids the link between understanding how we go from something that's prebiotic or non-biotic to something that's alive? Then spectral interpretation. So understanding, going to a body and really studying it in detail, understanding its chemistry and what the rocks there are like. I have to remember, where are we? Resource identification is the next one. So understanding whether small bodies can provide resources to humans, that we might be able to use those going forth to explore the rest of the solar system. And then the last part, the Rex part, is the regolith explorer. So all these small bodies that we have in the solar system, they're exposed to the vacuum of space, the harsh environment of space. And so their surfaces are constantly being resurfaced and reworked by being exposed. And so that creates this regolith layer, kind of a soil layer on the surface that can tell us a lot about the more recent history of those bodies. So everything we're trying to do on the mission and all the questions we're trying to address kind of is said in the name.
And so how do you go about it? So you have this spacecraft, and it's not quite a touchdown when you're talking about such a small object like, and I mean, is it more like sort of a game of tag? It kind of bumps into it and grabs a little surface material? I mean, how does that work?
Yeah, so the way I like to think of it is, or at least I imagined it was going to happen, was kind of, if you know what a pogo stick is, so kind of
Yeah.
if you're jumping up and down, you kind of touch the surface and then back away. And I think that's what we expected to happen. We were not landing on the surface. We were supposed to just touch very gently and then back away. And a lot of things on the mission didn't go according to plan. It's not that they were disastrous, but we were surprised, is how we like to say it on the mission. And it didn't quite go to plan, meaning we descended towards the surface. We were about to tag, and then we realized as we touched the surface, the spacecraft didn't stop. It kept going. It actually went about 50 centimeters into the subsurface, showing us that Bennu was really unconsolidated, really porous, and we weren't really expecting that, even from having orbited for 2 years trying to understand the surface. We didn't expect that, but navigated it and managed to collect the sample and back away safely.
And so sort of, was there like a plume of surface material that you kicked up through the pogo stick action?
And it was fantastic. You know, we dialed in. So all of this is happening, and we've got a kind of view on what's happening in the control room in the US. So we're watching that, and all of our colleagues, it was COVID, so everyone's got a mask on. So you can't see their emotions, even though you can kind of feel it. And it was, my memory, and I might have got this wrong, Jess, is that an awful lot of effort. When we got to the asteroid, there were boulders everywhere, and no one was really expecting that. And so, you know, all the thing has to do is move a little bit,
over or
and
something. Yeah.
and it'll smash up a solar panel, and then you're done.
done.
And so, getting the precise position to within less than a meter proved to be really, really hard. And the engineers did an incredible job of kind of building up an alternate way of positioning on the asteroid, and it worked fantastic. So I remember hearing, you know, plus or minus 50 centimeters, plus or minus 50, and then and I think I've got that right. And if it was basically about that, then we knew we were safe.
Right.
And so that was amazing. Yeah, it was fascinating.
And so you scoop up this material, and then, again, you don't quite blast off, you kind of push off, I guess, and head back toward Earth, Jessica. And is there a capsule that separates from the main ship that then drops back to Earth? How does that final step work?
Yeah, so first of all, the sample collector, when we backed away from the asteroid, realized that it was leaking, so we had to get it put away very quickly. It was a bit dramatic. And it went into a sample canister inside a sample return capsule that was on the spacecraft. And so when on, 24th of September last year, we jettisoned or ejected the sample return capsule, and it separated and made its way to Earth while the spacecraft remained intact and is actually now a new mission called Osiris-Apex, which is going to a different asteroid in the future. So yeah, those two things separated, and we ended up with 2 missions.
And so the canister falls to Earth, you gather it up, you bring it to, I gather, Arizona is where the analysis is taking place initially?
So when the sample return capsule was recovered, it was recovered at the Utah Test and Training Range in Utah, so a big military base. And actually it was met by a group of curation staff from NASA's Johnson Space Center in Houston, where they and the folks from Lockheed Martin, so that's the spacecraft manufacturer, they took apart very carefully the sample return capsule to reveal the canister inside, but inside of it had the sample contained in its own little container. And so then the curation staff put that canister under purge, under nitrogen purge, and then shipped that by a massive airplane to Johnson Space Center, where the sample is being curated and carefully processed. And that's actually where NASA keeps all of its astro material. So anything that's from outside, not from Earth, is kept at NASA JSC.
Now, I've heard that you had trouble getting the lid off
Yes.
of this. Is that correct? Is that true, Phil?
I'm so tempted to just leave that to Jess. It was, with the mission, it's a continual conversation between the engineers and the scientists. As Jessica said, a lot of things happen. It always pushes the limits of what a human can imagine on both of those sides, whether you're an engineer or a scientist. Basically, rather than trying to get a solution for a problem on Earth, you have no idea what to expect. And so the universe is the bar that you have to meet. In this case, the universe kind of tweaked us a little bit in that we had a problem undoing the screws on top of the canister, and that got stuck for a little while.
Yep.
So basically, colleagues at JSC actually had to come up with an alternate toolkit in order to take out the final part of we got a picture of some of it there, in order to take out the final part of the canister.
But bottom line, you get the lid off. And before we talk about what's inside, Phil, my understanding is that the generous folks at NASA gave you some of the dust on the outside of the canister.
Yes.
Is that sort of like, you've got the cookie jar and you've got the crumbs of Oreo, or is there, is that something that you expected, that you'd be analyzing the dust on the surface?
Okay, and I'm just going to be really thankful to. So basically, NASA is incredibly generous with sending this material out. They involved the world community of scientists, which is just gorgeous. Japanese do the same with their missions. In this case, it's actually modern analytical techniques. We can do an awful lot with, 100 micron
Very little
particle.
sample.
Yes, like 1/10 of a millimeter, and getting, when we got a 1 millimeter grain from a colleague of ours at Natural History in London. Wow, that's huge. We could actually see it with the naked eye. Yeah.
And so when you analyzed the dust on the outside, what have you found so far?
Yeah, so I think that, shall I get into, I'm just going to get into.
Sure.
So the thing that really fascinates me, and everyone has different areas of interest, and Osiris-Rex as a mission, has a huge long list of topics that they want, the people are interested in getting into. The thing that fascinates me is the actually just kind of old school chemistry of this rock. I'm originally a geologist. As a geologist, there's probably like 50 elements that you analyze for, and when we analyze Osiris-Rex, when we analyze Bennu, it's, if folks can imagine, if you have the sun and you get rid of all of the hydrogen and helium and all of the volatile,
which is most of the stuff
most
there.
of the sun, then there's a little bit left.
Yeah.
And that composition and the relative abundance of those elements is almost a perfect match to Bennu. And that's really fascinating to me. I love that.
So it's as if it's the sun minus the vast majority of the sun. Now Jessica, you've also obviously now gained access to the inside of the canister. I presume you've started to analyze that too. Are you finding the same kind of mix of ingredients that Phil was just saying?
Yeah, so before the screws were unfastened, another little bit of ingenuity on the curation side was they realized that the flap, the mylar flap, that was actually that piece of the hardware that was gaping open in space and actually leaking material to space, that was flexible. And so while they couldn't get TAGSAM completely open, I should say TAGSAM stands for Touch and Go Sample Acquisition Mechanism, TAGSAM for short.
Yes, of course.
While they couldn't get it open, the curation staff actually used their tweezers. So imagine everyone has stood down. We can't get into TAGSAM. Everyone's pulling their hair out, and there's processors in the lab with the sample. It's in a glove box, and they're just poking the mylar flap with their tweezers, and like, hey, this is flexible. We see stuff. We can pull some of the material out. Do you want us to do that? And everyone was like, yes, go ahead and do that, please. So we actually got some material out that way, and we're able to look at it, and the team got allocated some of that material early. And then, as you know, later on in February this year, we finally got the rest of it open. And so some of that initial material made its way out to the science team. And we see the same thing, as Phil just alluded to. The bulk chemistry is something I too am really interested in, because it helps us understand the genetic history of different bodies and how they relate to each other and how they're spatially related, potentially across the solar system. And so, yeah, we've been learning huge amounts just from the tiny amount of material we have so far, which is about 1 gram, I think, has gone out to the science team.
Now, is it surprising that the composition that you find is so similar to the sun when you go beyond the dominant ingredients in the sun? Is that unexpected?
It's so, the most of what we analyze from in terms of extraterrestrial material on Earth is in the form of meteorites.
Yeah.
And they're awesome because it's basically free material that's landing all the time. There's 60,000 meteorites in existence. There's only 10 that are so close to the sun's composition. Yeah. So Bennu is one of those 10. And the glorious thing is that all of those other meteorites have been affected by, like the Earth's atmosphere, or even by rain before they were collected. Bennu is the most pristine material we've ever brought back. So this is perfect for.
And so, Jesse, is it too early to begin to answer questions like the question of water, the question of organic molecules, the kinds of questions that one asks when one is trying to figure out whether the conditions for life are commonplace or rare?
It's not too early. We're starting to pick apart Bennu to its atomic level even. And so we have found out that, yes, Bennu is a water-rich and carbon-rich asteroid, which is what we expected when we picked the asteroid, so that's a good sign. It's also what we expected the sample to look like based on the remote sensing observations of the asteroid. And so we know now that Bennu is one of the most carbon-rich astromaterials we have in our collection. So it's really carbon-rich, almost 5% carbon, which is huge. And also we're starting to tease apart the water abundance and its isotopic composition, as well as getting into the nitty-gritty of the different types of organic molecules that are present. And Bennu is really organic rich. We gathered that from the remote sensing of the asteroid, and we're seeing that in the laboratory today. So to date, I think we've identified about 27 different types of amino acids in the return sample. And so it's still early days, but we're getting some indications of just the variety of organic molecules present.
So there's been a long debate about where water on Earth came from. And I know that this has gone back and forth over the decades. Was it comets that brought water to Earth? Was it asteroids that brought water to Earth? I remember there were studies, and I'm probably out of date, that the ratio of heavy water to ordinary water in asteroids seemed to better match the ratio that we found on Earth, which was sort of tipping the scales toward asteroids. Where do we stand on that, and does Bennu give us any further insight into that question? Phil, why don't you start?
Okay.
And then,
it does keep going back and forth, and basically you've got kind of one of three choices, so asteroids or comets, so those would be falling in after Earth had formed, and the other is, did we kind of
intrinsic,
did we accrete material that was then degassed, and people still fight about that. I mean, my feeling is with all of these things is probably a bit of all three.
Right. Any new insight, Jessica, or do you anticipate new insight into the question of Earth's water from the analysis that you're doing now?
Yeah, so one thing we can do is we can look at the isotopic composition of the water locked up in Bennu materials. And then we can also start to pick apart the samples themselves and look at different components and what their water content or isotopic composition is. And so we're not quite there yet, but some early indications tell us that the water inside Bennu is very similar to other types of meteorites that most closely resemble Bennu. As luck would have it, those compositions are also similar or within the range of Earth's water. So as I say, we're not there yet, but there are some hints that, objects like Bennu, possibly once in Earth's history, were delivering the types of ingredients that we needed: water, carbon, your favorite word that you mentioned earlier, the chomps elements, like they were coming to Earth, potentially in objects just like Bennu.
And so with 20, if I heard correct, 27 distinct amino acids already discovered in the sample, with water being part of this mix, how does that leave you thinking about the ubiquity of life in the universe? Does it feel to you that this is just something that is going to happen in a whole variety of suitable environments, or is it a one-off possibility?
I mean, for me, I think where I kind of go with that composition that's a bit like the sun, is that if you made planets from that material, we'd have, an ocean 40 kilometers thick. So you wouldn't have, so life kind of wants a combination. You want those boundary zones in between water and rock. And I think, when you think about the inner part of our solar system, we have rocky planets. A process happened to get rid of a lot of the volatiles out of that region. And we really don't know what that was. And so so that's one of the things that I'm fascinated with from a kind of how planets got formed point of view, because that process could be ubiquitous. So it's part of star formation and planetary system formation, in which case there's a region that is that nice boundary zone for life. Or we were lucky, and so getting the answer to that, I'm really interested in.
Right. And Jesse, are you going to hedge your answer too, or go out a little bit on a limb here? So what is your gut feeling based upon the scientific analyses that you have done both with this mission and previously? Life common, ubiquitous, special?
I kind of wave around like filled it a little bit. Certainly the ingredients for life, so the elements that we know make up, amino acids, proteins, cells, all of those ingredients are present in objects like Bennu and in other planetary systems. Clearly something special happened here on Earth to turn those prebiotic molecules, the water, everything, to create the environment needed for life to emerge. And as Phil said, we don't know what those processes were. We can't go from something that's abiotic to something that's biotic. And so when we go to Mars, there are some environments on Mars that we know were once hospitable and could have been habitable, but there's a difference between it being habitable and there actually being life. So I think we're going to get closer with Bennu to understanding what the precursors to life were. And that's a really important step in understanding our origins.
Yeah, for sure.
I can be more...
Yeah, please, feel free to...
I think life's everywhere. And I think...
Wait, you really feel that? You're not just saying that because I sort of pushed you a little bit?
No, honestly. So
Yeah.
I think complex life is more rare. And I think
Intelligence.
Self-aware, more right.
Yeah.
And
but microbes and things of that sort.
And I think in my lifetime we will either discover it or we will get a real sense of how lonely it is.
Yeah. Well, that would certainly be either way, a profound insight. Before we finish up this fascinating conversation, Jessica, you made reference to what this craft did after it dropped off the sample at planet Earth. You said it's going on, I guess, to another asteroid. Just tell us what that is and how that was chosen.
Yeah, so the Osiris-Rex mission changed into the Osiris-Apex mission, where Apex stands for Apophis Explorer. And Apophis is an asteroid different to Bennu, but similar to, if anyone remembers, the Hayabusa mission to asteroid Itokawa. It's a stony asteroid, so it doesn't contain a lot of, we don't think, a lot of water-bearing molecules or carbon-bearing molecules, but lots of silicate minerals. And it's going to rendezvous with this asteroid Apophis just after Apophis has a close encounter with Earth. So Apophis is going to pass very close to Earth, I think between the orbit of Earth and Moon.
Really?
Which is super close. So we're going to get a really good look at it, I think, in 2029.
Is that scary? I mean, scary close?
I don't think it's that scary. I mean, we have meteorites and asteroids that pass us by all the time. I don't think we need to be worried. But it'll be great viewing.
Yeah, for sure.
It's actually going to come within the belt of geostationary satellites. So it's going to come really close.
Wow.
Yeah, not scary. It was scary for a while. And then people did a really great job of being very particular about its orbit. But it is going to be really close. Yeah.
Wow. And Phil, are you looking forward to, will you be participating in the data, the samples that I gather are going to be taken from this other asteroid?
So that won't be samples. That'll be using all the other systems on board the spacecraft.
Because it's too rocky to be able to grab anything? Is that the issue?
It's a matter of kind of matching orbits. And then, so one of the incredible things with the Osiris-Rex and Bennu was that, these objects are orbiting the sun at, many, many kilometers per second. Matching that, by the time that, Osiris-Rex was coming up to the asteroid, it was like walking pace, which is, how those people managed to do that blew me away. That's a really good question if I'm involved in Osiris-Apex, because I'll have to ask my science group lead about that.
Not to put you on the spot, Jessica, but definitely I believe there is an entreaty here.
Yeah, it won't be collecting any samples because the sample return capsule is already on Earth. So there's no mechanism to collect the samples, but all the cameras and spectrometers and everything on board are in tip-top shape. So we're hoping to get some really nice remote sensing data of the asteroid. And I'm not part of that mission.
2029, you said
2029.
Well,
yep.
Exciting. All right, so maybe 2029, World Science Festival of Brisbane. We have you back to report on what's happening there. But please join me in thanking our two guests for a fascinating conversation. So thank you, Jessica. Appreciate it.